Hello and welcome to the lecture Advanced Model Specification with LASSO. My name is Hugo Storm and today I would like to talk with you about how we can make use of a machine learning approach, namely LASSO, for doing model specification in an econometric context, solving agriculture economics or environmental economics problems. What are the learning aims, or what is the structure of the lecture? Well, basically we have two sections. In the first section I would like to introduce LASSO and friends, so you should gain an intuitive understanding of what regularized estimators are, so what LASSO is, rich regressions are, or others. And you should also understand how LASSO can be used for model selection. In the second part, we would like to talk about how more specifically we can use LASSO for model selection. So we discussed several approaches for model selection. You should understand what the difference, or that there is a crucial difference between model specification for prediction tasks and for causal analysis tasks. We would like to draw the connection to model specification and econometrics that you have discussed before, so that you understand the connection. And I will introduce the concept of, or the approach of Post-Lasso, and you should understand how that works and also understand its limits. And we're also finally discussing better approaches for model selection using LASSO when doing causal analysis. So that's the plan for today. So let's start right with section 1, discussing what LASSO actually is. Okay, to start, let's look what this LASSO thing is about that we wanted to consider today. And before we look into the formulas, which look more complicated than they actually are, let's try to understand LASSO from a very intuitive perspective. And for this, I would like to ask you to imagine that the regression coefficients, the OLS regression coefficient that you have used so far, would cost money. And as typical, if something costs money, you're facing the problem that you need to decide how to spend a limited budget in a most sensible way. And you can spend your money on the regression coefficients in your OLS regression. And what you want is that you would have a good fit of your regression line to your observations, and you want to use your budget in such a way that you obtain a good fit. And that exactly is the question that LASSO or every other penalized regression is trying to solve. It's doing a budget allocation, so to say, in a regression context. Let's look at that more formally on the right. So the first line, that is something that you should know already. That is the usual sum of squared minimization problem formulation. So we have here a regression with p variables. We have beta 0 as our constant, and then the betas for the vector of betas for our regression coefficients, and we want to minimize the sum of squares by choosing the betas in an optimal way. So that is completely equivalent to what you have discussed so far and what is familiar to you. What is different is the second line here that says that we want to do that minimization subject to a constraint, subject to our budget constraint. And that constraint ensures that the absolute sum, so that is this one here, the absolute sum of our regression coefficients are lower or do not exceed our budget t. So, and that is new. So far you could choose the betas in whatever way you want. In LASSO you can only choose them in such a way that the sum of absolute values is smaller a predefined budget t. You can also formulate this in Lagrangian, as you might know from your microeconomics class. So that reads then as such here. The LASSO estimates, beta hat LASSO, are those betas that minimize this expression, and that is simply again here our sum of squared residuals formulation. plus these added penalty term, which is simply the absolute value, the sum of absolute values of your coefficients times your penalization parameter lambda. So which would be in microeconomics, which would be equivalent to the shadow prices. So that is the basic idea of Lasso and also the formal representation. Okay. So second thing, let's look at how that things perform in action. So why is that useful for doing model selection? And to do so, it's important to understand the role of the tuning parameter lambda. So that is the regularization parameter that basically determines how large your available budget is. And the crucial thing is that Lasso can force certain parameters to zero, and in this sense performs variable selection. And that is what you see on the right here in that plot. And you read that plot in the following way. So for now, let's ignore the x-axis, simply assume that this x-axis is inversely related to the available budget lambda. So that means that if you go from the left to right, the available budget increases. Yeah. So that means that on the right, you basically have a situation where you have an unlimited budget, which is equivalent to a simple OLS regression. And how you would read the plot here is that under this unlimited budget, if you check here the values for your 5 coefficients, this graph tells you the absolute value or the value of your coefficient. So that means for this variable here, HS, you obtain something around -6, for college something 0.5, for those two around 5, and for those two around 11, 10, 11. And this graph is now showing you how the values of the coefficients would develop when decreasing your budget. Yeah? So if you go from right to left, you're decreasing your budget, and the plot shows you how the coefficients would develop. And you see that they all get smaller, and at a certain point they are dropped. They are exactly 0, and they are dropped from the specification, so to say. So for example, if you consider that college variable here, if you decrease your budget a little bit, so going from an unlimited budget to a somehow restricted budget, then the first thing that Lasso is doing is that it stops spending money, so to say, on the college variable. Yeah, so the college variable, college coefficients goes to 0, so basically that variables drop out of the specification. And the further you decrease your budget, you see that other variables drop out as well. So this variable then drops out, then this one here. And finally, at that point, all variables are basically pushed out of the model. That is, if you have a very limited budget, then you can only afford basically to include a constant, and everything else is dropped from the model. So, and that is important. So that is the way that Lasso performs model selection by choosing different values for your available budget. So the lambda, the tuning parameter, you can define basically, or you can use that variable to drive out certain variables of the model, and you see which variables are dropped first, which gives an indication which variable is less important than another. So that is Lasso in action, and that is the property that we want to use in the following to devise sensible and useful model specification approaches. Maybe just for completeness, what do we have here on the x-axis? I said that this is inversely related to lambda, and that is basically everything that you need to know and is sufficient. But for completeness, exactly what is displayed here is basically the ratio of the absolute values of the Lasso coefficients over the absolute value of the OLS coefficients. Yeah, so that means that you basically scale the range over which you vary your lambda parameter. And that means that at 1 the LASSO coefficients are the same as the OLS coefficients, and at 0 you have driven out all the LASSO coefficients of the model, so they're all 0, and then everything else in between. Yeah, so you're scaling the range over which you vary your lambda parameter. You also see other versions of that path variable or coefficient path dependency plot also in the lecture, but also in other books or depending on the package you're using. But the important thing is that the x-axis is always related somehow to the available budget, so the tuning parameter lambda. Okay, so now that you have seen how lambda works, so what the role of lambda is, the next natural question is how to choose lambda in the most appropriate way. And lambda is a hyperparameter to the model, so a parameter that needs to be set by the user, and that is something that is very common for machine learning methods, and the machine learning community has come up with all kinds of ways of how to determine the optimal values of these hyperparameters, of these parameters that needs to be set by the user. And I will briefly try to introduce these methods so that you have at least an intuitive idea of how to go about these approaches. And the first important thing to recognize is that machine learning approaches were primarily developed for prediction purposes, and we are coming back to that also in the second part in more detailed. But here it's important to recognize that fact, and what machine learning people are interested in, they want to have a model that generalizes well. So that generalizes well means that it makes a good prediction for an unseen new sample point. And that's the only thing that is relevant. And what we are aiming to is to choose the hyperparameters in such a way that we are doing well in these out-of-sample predictions. And that can be most easily illustrated with an example. So consider here on the right here, consider the example that you want to predict happiness from wealth. Yeah? And you have more or less 3 different model specifications, and the question is what is the most appropriate specification to choose. On the left here we see we are trying to fit that the observed values by a linear function. And we might conclude that, well, that might not be flexible enough. We are not really capturing the nonlinearities that we see in the data. On the very right, you have something that is very flexible, that is perfectly approximating your observed samples. However, you might be worried that this is too flexible and that this is overfitting to the observed sample. While in the middle, you have something that looks quite right, so that is nicely capturing the nonlinearities without overfitting to the observed data, and that's basically where we want to get at. So the question is, how do you determine that point? And what is typically done is that you split your sample in 2 parts. One part, that's called the training set, you use for estimating your model, and the other part you do not use for estimation. You leave that out and you use that to evaluate the out-of-sample prediction error. Yeah, so the prediction error for an unseen new sample not used during estimation. And what you typically see then is that what is given here on these 2 lines here, the error in your training set, so in the set that you use for estimating your model, that is constantly decreasing with model complexity. And that's what you also see here. That model is better than this one here, and this is even better than that one here, so that here you basically don't have any errors in your training set. You're perfectly fitting your observed values. Yeah? So this is constantly decreasing. However, the out-of-sample error, and this is this upper line here, that is also high in the beginning, where your model is not flexible enough, then decreases up to a certain point, which is basically the optimal here, and then starts to increase in the range where you are starting to overfit to the trained data. And this function you use in order to determine the complexity of the model. So you're choosing your hyperparameter where this out-of-sample error is basically lowest. Yeah? And that is this point here. In terms of lasso, that means our model complexity is tuned by our regularization parameter, by our lambda. So that means here lambda is really, so the available budget is really low, so we are very restrictive, meaning in the extreme case that you only include a constant, and then if you move to the right, you are starting to allow variables to come into the model, so you are increasing your budget, so to say. Yeah? And what we want to find is that point where the out of sample prediction is lowest, the prediction error is lowest. Yeah? So that's the basic idea that you're choosing. There is one other variation of that, an extension of that is important for the application later on, and that's typically used, and that is something that is called cross-validation. Here the idea is simply that you basically repeat the process that I've just described several times, and specifically, for example, if you're doing 5-fold cross-validation, then you're splitting your sample not in 2 parts, you're splitting it in 5 parts. You leave out 1 part and use the other 4 parts for your estimation, calculate the out of sample prediction error for the left out part, and then you repeat the process by leaving out another part and using the 4 other parts for estimation again. And you're repeating that process for each time leaving out 1 other part, and then you're calculating for each part the out of sample prediction error, average that prediction error, and obtain an overall prediction error. So that approach is, particularly in small samples, more efficient than doing the split just once. Yeah? And you will see in the examples later on how that works in practice. There is a lot more on that, but I will leave it as such. And I think that's sufficient to understand how to work with these lasso approach. Yeah? So that is the approach that you choose or that you take in order to choose the optimal lambda when you're interested in a good prediction. Okay, now that you have seen how lasso works and also how to choose lambda in an optimal way, let's talk about what makes lasso special compared to other penalized regressions. The special thing about lasso, which is important for our aim to perform model selection, is that the obtained result is sparse, which means that it forces some coefficient values exactly equal to 0. So it not only shrinks variables that are unimportant, coefficient values that are unimportant, it shrinks them and at some point it sets them exactly equal to 0. And not all regularized regressions achieve that property. And that property is important for variable selection if we want to really determine which variable is included or is not included in the model. Yeah. So what are other regularized or penalized regressions? And let's consider this expression here again that you have basically seen before, with the difference now that we have these little q in there, and that q can take on different values. So for lasso, that is equal to 1, which is the expression that you have seen before, which means that the penalization term here is the sum of absolute values of your coefficients. But you can choose also other values for q, and that results in other penalized regressions. So for example, a common choice is q equal to 2, which would mean that this expression here is the sum of squared coefficient values. Yeah? And that is the rich regression. Yeah. You can also have q equal to 1, which is then equal to 0, which is then best subset regression, or you can have all kinds of combinations or other values as well. So one thing, for example, is the elastic net, which is a weighted combination of lasso and rich. You see that here you have this term alpha, which basically weights lasso against rich. So here this expression is the sum of squared coefficients, which is rich, and this is the sum of absolute values, which is lasso, and you weight them together to a penalty term. Yeah? So that is also something that you see quite often. There is also something called adaptive lasso that results in models that are even sparser than lasso, which is quite attractive, and there is something like a group lasso, which selects groups of variables which is again a bit different. The important thing here is that you can use that, for example, if you have a set of dummy variables that specify a specific characteristics, then you might not want to include individual dummy variables, but you rather want to have them included as a group or excluded as a group, and that's something you can achieve with Lasso. Let's briefly come back to these sparsity considerations. The important point why Lasso obtained a sparse result is that it constrains region is linear, and you see that here. This blue thing here is the constrained region for Lasso, while this is the constrained region for Rich, and here are also examples for other values of Q and the constrained regions. Yeah? So for example, best subset selection would basically look like this, and that is in principle the ideal case. So ideally we would try all combinations of our parameter values and see which results in the best model. However, computationally, that is infeasible if your number of variables exceeds a certain number. Yeah? So that is computationally very difficult. And what Lasso achieves is that it obtains a sparse solution, so selecting individual variables, but by still having an objective function that is still convex, so it's computationally still attractive, so to say. So and what that sparsity conditions means in practice, that can most easily be illustrated when looking at these coefficient plots that we have seen before, comparing Lasso and Rich. And that is what is given here on that slide. So this part here you have seen before, yeah, as we have discussed before, that shows you how the coefficient values developed when changing lambda. And you see that here for Lasso, and you also have that here for Rich. So again here, this is the result that you obtain for an unregularized regression, so for OLS, and going to the left, you see the result for Rich when increasing lambda. So you see how Rich changes the coefficient values, forcing them to 0. And importantly, comparing both of them, you see that Lasso achieves a solution where it's set at a certain point, sets coefficients exactly equal to 0, while that never happens in Rich. Rich keeps the variables, it only forces them to be really close to 0. From a prediction purpose, or from a model performance purpose, the difference between the two is not that important or not that large, so to say. But from a model selection perspective, the difference is quite important and fundamental to have these sparse results. Okay, finally, I've prepared, so to end section 1, I've prepared an R example showing you how to predict housing prices that builds on an example also from Verbeek, the econometric books that you're using. And hopefully that helps to get an idea of how technically to implement Lasso, doing the cross-validation and using that in a prediction context. You can go through that notebook, this R notebook, on your own, and I'm happy to discuss questions or all other things in the Q&A section that we will have. Okay, so then going to the second part, now that you have seen how Lasso works, how it performs model selection, let's talk about how you actually use this Lasso tool for doing model selection in an econometric context. And the first thing that we need to discuss here is, or that I wanted to make clear here, is that it is really fundamentally important to distinguish what the purpose of your task that you're doing is. So is it a prediction task, or are you interested in causal interpretation? And I think that is really core to understand what you're aiming for, because on it a lot of things depend, particularly in terms of model specification. So what are the difference between the two? In prediction, we are focused on the out-of-sample prediction performance, as we have discussed before. So what we want is a model that performs well for an unseen new sample point, so it performs well out of sample. In a causal interpretation context, we are interested in identifying the underlying relationships. And that is fundamentally different. And being good in an out-of-sample prediction task does not necessarily mean that we are good, that the model is also good in terms of identifying the underlying relationships, and also vice versa. Yeah? So that's the first important thing. The second important thing is that in a prediction context, you're not interested in interpreting the coefficients as such. Yeah, you don't care what the coefficient values are, you're not looking at the coefficients, you only take the model to do a prediction. Yeah. While in a causal interpretation context, all that is of interest to you are the coefficients. So you want to interpret the coefficients as a marginal effect. That is your main result. And that's really important to keep in mind. The third important distinction is that in a prediction task, you can measure the prediction error. You can always measure how well you are performing. So you can put a number on the model performance. In a causal interpretation task, that is way more difficult to measure how good you are in terms of model selection, and the consequences of doing errors in model selections are much more important. In prediction, you don't really need to care about all the theory, about the problems, you're only interested in one number. So you boil down the model to one single number. And you can always measure that number and say, okay, I went from there to there and that is better, therefore my model is better. In a causal interpretation context, that is way more complicated, assessing how well you are performing and saying which model is better than another. The prediction context, that's basically the machine learning world. So I would say 95-98% of machine learning applications are prediction tasks. And to some extent they are way simpler than causal interpretation tasks, which is the econometrics world. And this distinction is important, and it's also important to recognize that problems are not always as easily to distinguish that is really a prediction or a causal interpretation task. And you really need to be aware of the differences and make sure that you understand what you're dealing with. So as an example, consider the housing prediction price example from the R notebook from section 1. This problem can be considered both as a prediction task but also as a causal interpretation task, and they are very similar to a certain degree. And in the section 1 example, I framed that example as a prediction example. Yeah? So in this R notebook, we assume that we want to predict house prices. However, in Verbig, the example was originally motivated differently. There it was framed as a causal interpretation task where we were aiming at estimating a hedonic pricing model where we could interpret the coefficient values as the contribution of the individual attributes of the house, so what contribution these attributes make to the selling price of the house. So we are interested in the basic question of how much higher is the price if I add one additional bathroom. Yeah. And that is, in both cases, we have prices on the left and we are predicting prices to a certain degree. However, in a pure prediction task, you're only interested to make a prediction of what is the selling price of the house given its characteristics. And you want to get a prediction that is as good as possible. But you don't care about which of the attributes contribute to the individual predictions or to the individual prediction. In a hedonic pricing model, you are in a causal interpretation context where you are interested in saying, okay, that attribute of the house contributed that much to the overall prediction price. So the problems sound very similar, look very similar, but they are fundamentally different in terms of the objective that we want to achieve. And I think that needs to be really clear before you make any decision about the model selection strategy that you are taking. Okay, so now that we have clarified that, let's discuss why are they so different beyond the point that I've mentioned before. And the most crucial point is in terms of the issues of omitted variable bias. And that is something that you have discussed also before, and that was stressed before, and that is really important in econometrics. But interestingly, it is not important at all in machine learning, and that is because they are only dealing with prediction tasks, and in prediction tasks you don't really have omitted variable bias. So that is something that doesn't exist because you're only interested in getting a good prediction. But as soon as you want to interpret your coefficients in a causal manner, you need to worry about omitted variable bias. And because that is what we usually do in econometrics, omitted variable bias is so important in econometrics. Okay, so let's have a short recap on what omitted variable bias is. And you have discussed that in the last lecture. So omitted variable bias results if you have an omitted variable, so if you omit a variable, if you leave out a variable that is correlated to your dependent variable and one of your or more of your explanatory variables. And that and is important because that means that you will not have omitted variable bias if the omitted variable is only correlated to the dependent variable but not to one of your explanatory variables. And you will also not have omitted variable bias if your omitted variable is only correlated to the explanatory variables but not to the dependent variable. So you need to have both in order to have an omitted variable problem. Yeah. Okay, so that's important. So that means that variables that do not cause an omitted variable bias can be omitted from the specification. Yeah. But what you need to watch out for are those variables that do create an omitted variable bias. So that's the first thing. The second thing is that the bias increases with increasing correlation to the explanatory variable. So the higher the correlation gets, the higher the bias will be. And let's consider that in a very simple stylized example. So assume we want to explain wages by age and work experience. And we are primarily interested, or we are only interested in estimating the causal effect of work experience. That is what we want to determine. Yeah. And what you can imagine is that age and work experience, they will definitely be highly correlated. Older people will tend to have more work experience and vice versa. Yeah. So these variables will definitely be highly correlated. And if you drop age, then that will be an omitted variable, which is likely to be correlated to work experience and also age. Yeah. So that would be an issue. So you would not want to drop that variable if you want to interpret work experience, the coefficient of work experience, in a causal way. Okay. So, but now consider what Lasso is doing. Lasso is programmed to do prediction, and it's programmed to drop variables that are highly correlated, which means that they include the same information for prediction. So what Lasso is doing, it checks systematically in all kinds of ways how to drop variables that basically contain the same information, i.e. that are highly correlated with each other. And that perfectly makes sense if you are in a prediction context, and that is what Lasso was developed for, but it might not if you are in a causal interpretation context, as we have just discussed. Dropping age in this example here makes sense from a prediction purpose. From a prediction perspective, it might not really add much in addition to work experience, but in terms of the causal interpretation, it might be something that you would not want, that you drop age from that specification here. And the problem is that, so ideally we would want to have a model selection approach that selects really those variables that matter and that does not include an omitted variable problem. So we would want a procedure that includes all variables that matter for y, and then we would not have an dependent variable problem. The problem is that in practice we cannot rule out errors in model selection, and those errors would then automatically or directly lead to omitted variable bias, and therefore we would want to have model selection procedures that are more robust and protecting us from these kind of biases. Okay, but before we come to that more robust approaches, let's assume that Lasso would be able to recover the true model without any omitted variable problems. And actually, the theory behind Lasso is actually quite optimistic that Lasso is capable of doing so. So what the theory tells us is that under certain conditions it can be shown that Lasso is able to recover the set of variables that are in the true model, which means that Lasso has the Sparcistency property, or even better, that it has the oracle property, so that it is able to recover the true model. And there are also approaches like the adaptive Lasso that can be shown that they recover the true model and even more under even more general conditions. So what are these conditions? Again, only discussing them here in an intuitive way. The conditions are that the true model is sparse, so that the true world is linear and sparse and simple. And that the true model is a subset of all the available variables. So let's say you have 100 variables, then the true model needs to be within these 100 variables. And our aim is to find those variables that are in the true model. If we're able to find them exactly, then we will not have an omitted variable bias and everything will be fine. The second condition is that and that is even more critical, is that the correlation between the variables is not too high. Ideally, the variables needs to be nearly orthogonal. Yeah. So that is what the theory tells us. Under these conditions, Lasso will be able to recover the true model, the set of variables that are in the true model. The problem is that these conditions are in practice, they are not trifle, so you can, particularly these not too high property, you can assess in Monte Carlo simulations how high the correlation can be. And it turns out that that really needs to or cannot be too high. Yeah? So the bar is not very high, I would say. And additionally, it is difficult to check if this bar is reached in practice or not, because in order to check that, you would need to have the true set of variables which you want to discover in the first place. So in practice, even so, these theoretical properties are really attractive, not only by the name, but in practice they are difficult. They are difficult to met, and they are not possible, and it's not possible to check these conditions. And particularly these near orthogonality assumption is difficult if you are in the context where you have very many observations or very many variables that you would want to include in your model selection. Because in such a high dimensional context, it's very likely that your variables will be highly correlated. And that is a setting where you're usually operating at, because you would want to use Lasso in settings with a very high number of variables. If you only have a small set of variables to begin with, then you don't really need Lasso to do model selection. So you would rather use Lasso in a setting with large number of variables, and in those settings it's very likely that you have high correlation between your variables. So that is a problem. So it is unlikely that these conditions, these theoretical conditions, are met in practice. We cannot check them, and if these conditions are not met, then it's likely that we are not capturing the set of true variables and that we are suffering from omitted variable bias. Nevertheless, let's assume that these conditions are met and that we are using Lasso to do model selection. There is one additional aspect that you still need to consider. Yeah? So even if these conditions are met, then you need to be careful when using Lasso for model selection, because Lasso is not only selecting variables, so having the sparse property or leading to a sparse result, but it's also, because of the regularization, it's also forcing all variables, it's shrinking all variables close to or closer to zero. So that means it's systematically including or introducing bias in your coefficient estimates. And let's consider these coefficient plot here again. What you see is what we have discussed before, that Lasso is pushing variables exactly to zero, but also for those that are still in the model, like this one here, when you decrease your available budget, then you're forcing variables that are still in the model closer to zero. Yeah, so you're systematically including bias in your estimation. And if you want to interpret your coefficients, that is obviously something that you do not want to have. So therefore, be careful when interpreting the coefficients of Lasso at the true marginal effects, or not being careful, don't do that. Yeah. Okay, so even if the theoretical properties are fulfilled, Lasso can theoretically be shown that it results in the true model, but you cannot interpret the coefficients directly. Yeah. And that is where post-Lasso or relaxed Lasso comes in. So that is actually a problem that we can rather easily fix. So even if we want to interpret our coefficients as the marginal effects, and then the theoretical conditions are fulfilled, then we would do the following. We would simply take a two-step approach where you would first use Lasso to determine which variables to include in the model, and then take those variables in a second step and run OLS again, including only the selected variables. And as such, you would exclude or you would eliminate the regularization bias, the tendency of Lasso to push the coefficients towards zero in this second step. Yeah. So that is a really simple, straightforward approach. Take your model, include all variables in Lasso, perform model selection using Lasso, determining the optimal specification using cross-validation, get the set of variables that are included, that Lasso includes in the model, take those variables and run OLS again, and then you have an outcome where you can interpret the coefficient as a marginal effects. Yeah. So that is theoretically very attractive if the conditions are fulfilled, and it's also technically very attractive, so that's a really simple approach that you can directly apply. Does that solve all our model specification problems? Does that solve everything? Is that the approach that you should always take? Well, in practical settings, as we have discussed, you should be careful because it is likely, if the conditions, the theoretical conditions are not fulfilled, that you're not recovering the true set of variables, and that you are by that including omitted variable bias, which can be an issue, or which are an issue when you want to interpret your coefficients in a causal manner. So therefore, post-Lasso is attractive, but is something that should be used with care, and you should really make sure that you understand its limitation. So ideally, we have an approach that is more robust than this post-Lasso approach, and that's what we will discuss next. So, and that approach is an approach that is called double selection, that was developed or proposed by Bellonie et al. In 2004, a paper that I've also have in the references and is really recommendable. It's also easy to read, it's rather accessible, and comes also from an econometrics perspective. And the approach is the following. So assume that we are interested in estimating a treatment effect, alpha. So assume that you are in a context where you're really interested in estimating the effect of one variable. Yeah, so let's come back to our wage example. So let's say we are interested in estimating the causal effect of work experience. We are not interested in anything else. We are only interested in the causal effect of work experience. And then this work experience would be our treatment, so to say. So we wanted to know to what extent wage changes for an additional year of work experience. So the causal effect of work experience. Then in this setting here of double selection, work experience would be our variable D, and we would be interested in estimating alpha. We also have a set of control variables X that would include age, gender, the profession, whatever you want to include there, and we have a set of errors. Secondly, we assume that work experience is also a function of our characteristics. Yeah? So the work experience is also a function of age, of gender, of the profession, and so on. Yeah? So that means that D is to a certain degree endogenous. Yeah? And as we have discussed before, as soon as we are dropping variables in the specification in X that are related both to D and to Y, you would introduce an omitted variable bias. So that is something that you really need to want to guard you against. So and the idea of double selection is that we derive reduced forms from that. So you would simply in this first expression replace D and then solve for all the exogenous variables so that you really explain wage by everything else except for D, so for work experience. And we want to have as a second reduced form basically what we have above, also work experience explained by all the confounders. So and then the idea of double selection is that you take these two reduced forms and run Lasso model selection on each of them. Yeah, so you explain wages by the confounders and work experience by the confounders and apply Lasso, and you select those variables that are relevant in the first case and those ones that are relevant in the second case. And then from there you would take the union of these selected variables from both steps and run in a second step OLS on the union of those selected variables. Yeah. So the intuition is that you want to select variables that are relevant both for treatment D and for the outcome Y in order to limit omitted variable bias. So what you really want to guard against is that you are dropping variables that are only partially, mildly relevant for Y, but highly important for determining your treatment D. If you would only run Post-Lasso basically, or Lasso model selection on the first page, then it's likely that you're dropping variables that are only weakly relevant for Y, but are highly relevant for D. And that is what you would not want, because if as soon as you do that, you would introduce omitted variable bias. And vice versa, you also don't want to exclude variables that if you run model selection only on the second step, you would also don't want to exclude variables that are only weakly relevant for D, but highly relevant for Y. Yeah? So you're basically trying to select all variables that are relevant for both aspects that you're interested in. Yeah? Yeah, so that is more robust. It can be shown that this approach is more robust to omitted variable bias, and it's also something that is rather technically rather simple to run, and I think that's an attractive approach when you're actually interested in causal interpretation and want to use Lasso for model selection. Okay, finally, as in this first section, I've also prepared an R example showing you how to perform Post-Lasso and double selection in the context of estimating the effects of schooling on wage. That's also an example from the Verbig book that you might have seen in other lectures as well, or you will see in other lectures. Yeah, and again, we can discuss questions in the Q&A session. Maybe as an information, it might not be the perfect example for using double selection, because it is an example where you have very few observations or very few variables in the first place. So it might not be the case where you would usually want to apply Lasso. That is probably something, or the situation where Lasso is probably more useful is a situation where you have a rather large number of variables. But I think or hope that it's still helpful to see how these two things perform in a setting that is familiar to you and that you have seen also in other settings as well. Okay, finally, to conclude and to define some takeaway messages. So as we have discussed, one important point is that model selection for prediction is very different than model selection for causal inference, and you should understand why that is the case. Lasso is very useful if you do model selection in a prediction context. So if the aim is prediction, then Lasso is the perfect choice, and that is where Lasso was developed for. However, if you are doing model selection in a causal interpretation or causal inference setting, you need to be more careful. First, due to the regularization, you cannot interpret the Lasso coefficients directly. You have seen how to solve that, and that is Post-Lasso. Also technically, theoretically, very attractive and technically easy to implement. However, it is likely to suffer from omitted variable bias. And the consequences we have discussed as well. So that is therefore this approach needs to be handled with care, because the theoretical properties of Lasso are difficult to check in practice. Yeah, so be careful with that. And we have also discussed an approach which is called double selection, that is also technically easy to implement and is likely to be more robust to model selection. It is an approach that is particularly useful if you have a large number of controls or a large number of variables. It can even be applied in situations where you have more variables than observations, so a negative degree of freedom, so to say. And I would say it's also particularly useful if you are in a setting where the theoretical basis for your model selection is weak. So if you have a problem where there is a clear theoretical foundation and it's pretty clear which variables to include and which not to include from economic theory, then this is still the way to go. Base your model specification on the theoretical information you have. However, when you're operating in a setting where the theoretical basis is weak, then an approach such as Lasso is useful. Okay, and the final thing, some reference. So first of all, there is a book by Hesti and Tipcherani that is where I've drawn most of the examples from this lecture on. So that is an entire book on statistic learning with sparsity, so on Lasso basically. So that is definitely highly recommendable. And the other thing is the Bellonie et al. Paper introducing these double selection, which as said before is also very accessible and useful. So therefore also highly recommendable, and two others as well. Okay, with that I wanted to close. Thanks for your attention, and I'm looking forward for the questions and discussions in the Q&A section.